The seafloor and its sediments. There are different ways to measure the depth of the ocean. In early times, Poseidonus was one of the earliest from Greece. He used a large rock on a rope and lowered that down into the water to get the depth. So that line, that rope, can be marked with increments, fathoms, about 2 meters in length. And you could count the fathoms and then multiply and figure out the depth. In deep water, lowering that line and bringing it back up would take many, many hours, and they would maybe spend a whole day getting one measurement. By 1895, about 7,000 measurements deeper than 2,000 meters had been made. That's really a significant amount of measurements at that depth. Only, though, about 550 measurements that went deeper than 9,000 meters. These days, we can use an echo sounder or depth recorder to get the depths, and we'll go over what that means. And we also have satellites that measure the sea surface elevation, so changes in the level of the ocean. So an echo sounder, a little more high-tech than a rope. A ship would make a sound, having like acoustic equipment, and this sound would go down to the seafloor and bounce back. If you know the velocity of sound in water and you know the time it takes that sound to bounce, you can solve for depth over here. You also have to divide it by 2 because the sound is going down and back up. And then it can make a profile like you see on here on the right, that is a profile of the seafloor. Okay, so these days they would have an hydrophone array, so it would be a series of these recorders dragged from behind a ship. We also use a GPS, global positioning system. That's an array of satellites in the sky that tells us exactly where they are, so the ships use a GPS. They can do swath bathymetry, so using a whole ray to figure out the depth. They have echo sounders, ROVs, little vehicles that unmanned, that could go along the bottom and get the specific topography and the location that they're looking. So there are different ways, and they record at different scales. Over here on the right is showing the satellite imagery. So satellites can get the height of water, and the height of water actually changes over, like this is a little seamount. The height will be a little higher over that seamount, and so those kind of really accurate measurements can be taken by a satellite. Okay. Let's look at different parts of the ocean basin so that we can talk about the sediments that are found there. Here is a map of the world, and the open ocean is in the darker blue. The very light blue along the edges of the continental margins, these are the continental shelves, and they are thicker or thinner in different places. So the continental margins can be classified as either being active or passive. A passive continental margin is not at a plate boundary, but an active continental margin is at a plate boundary. Those are going to look really different on the, let me turn off my face. On the left is a passive continental margin. This is going to have a broad continental shelf, a continental slope, and a rise that comes up to that slope. That all leads down to the abyssal plain. An active continental margin is going to have an abyssal plain, but it's going to have a trench where the oceanic crust is going down into a subduction zone here. That's going to be marked by a trench. The continental slope is going to be differently shaped. There's going to be no rise because those sediments are getting consumed down into the trench. the continental shelf is not going to be nearly as defined and broad. The image below is a cross-section across an area that has a passive margin leading into a mid-ocean ridge with a little rift valley in the middle, going over to a series of seamounts, and all of that is getting subducted down into this trench. So the top two figures are blow-ups of the active margin with the trench and the passive margin with the well-developed shelf slope rise. All right, so here is a profile specifically across the Atlantic Ocean. We start with the North American side, the broad continental shelf, slope, and the rise up to it, down to the abyssal plain dotted by seamounts, up to the mid-Atlantic, the mid-ocean ridge or the mid-Atlantic ridge with its prominent rift valley here, more seamounts, Azores, some islands, over to Africa, and again a shelf slope rise. Okay. Looking a little bit deeper into the geometry here of the continental margin on a passive margin, the continental shelf has a very low slope. Then we have the shelf break, that is the edge of the shelf, down to the continental slope that has a steeper angle to it. And then the rise is going to be the sediment that falls off the shelf, cascades down the slope, and settles out on the edge of the ocean floor. So the ocean floor is going to be pretty much flat. The shelf is flat, the ocean floor is flat, the slope is the steepest part, and the rise is less steep. The shelf can be exposed during ice ages, so when sea level drops, that low topography, low relief allows for the exposure of the continental shelf. The slope has sediments that cascade down from the shelf. It can be muddy or rocky depending on the nature of the geology in that area, and also can be cut by submarine canyons. Turbidity currents are currents of sediment that fall off the shelf. We'll look at those in a minute. Here's the minute. These are turbidity currents. So at the edge of the shelf, the sediment can be unstable, and these sediments are going to cascade off the edge of that shelf. When they settle down onto the rise or the edge of the ocean floor, they're going to settle down with the largest grain size falling out of suspension first, and then the smaller grain sizes slowly being deposited. What that results in is something called graded beds, where the largest clasts are on the bottom and the smallest are on the top. They tumble down the slope. It's kind of like a submarine landslide of sediment. They can flow really fast and move out pretty far from the edge of the shelf. And they are often triggered by earthquakes or storms. So there's instability there, but then also something's got to get that sediment moving. So it could be an earthquake or a storm. Then the sediments get deposited down onto the slope and the rise. That's going to make a deep sea fan on the rise, and then it's going to have those graded beds. Oh my gosh, my face keeps being in the way. So here's a plume of sediment that it would look like on the seafloor. And here is a look at what graded beds look like. Let me turn my face back on. Hi. Graded beds. So at the bottom are the coarser class and fining upwards into finer grained sands. Graded beds. That graded bed is, once it has formed there, maybe when it lithifies, turns into rock, we call that a turbidite. So the bed is a turbidite, the flow is a turbidity current, pebbles, sand, silt. Okay, clay. That's that finding upward sequence. All right, I mentioned submarine canyons earlier in the edge of the shelf and going down into the slope. So this would be a submarine canyon. They're usually associated with river channels above sea level. So here's a river coming in, and here's a little delta, and then that channel continues under the sea through the submarine canyon and out onto the rise. And this shape here, this fan shape, would be where sediments are coming out of the canyon and depositing onto the rise there. So the canyon could form when there's changes in sea level, right? So if sea level drops during an ice age here, this river would continue out onto the shelf. One of the biggest submarine canyons out there is the Monterey Canyon in California. So here is the shoreline and this giant canyon coming off of California. And here's the topography of it as well. Taking that topography here and overlaying it on top of the kind of color-coded relief map. Okay, that leads out to the abyssal plain. The abyssal plains are on this map in the darker blue. So lighter blue, like on in the Atlantic here, I'm tracing the outline of the mid-Atlantic ridge. The areas around the ridge are going to be the abyssal plains, and then that leads up to that topographic change where we go from the rise up to the slope in the shelf. So abyssal plains cover approximately 30% of the Earth's surface. That's it's not half, but it's a big part of the Earth's surface is abyssal plains. And these range in depth from 4,000 to 6,000 meters. They're covered with clay. Clay is the finest grain clastic sediment. It's usually going to be wind-blown clays that have settled on the sea surface and then very slowly make their way down to the sea floor. And look at that rate, 2 centimeters per 1,000 years. Very, very slow accumulation rates of clays on the abyssal plain. Within the abyssal plain, there are some topographic features: islands, seamounts, abyssal hills. There's just the seamount versus abyssal hill is just how tall is it. Guyots, these were once islands that have now eroded, and so now they're flat-topped, basically flat-top seamounts. And then there's also dotted with coral reefs. This is an image showing what a delta might look like. So this is a very small scale. There's a little knife for scale. And we have a river channel coming in, and the fan here is a delta going into the sea. And then off the edge of this are little turbidity currents. There's the river, the delta, the shelf, the slope, the rise, canyons over here on the right. So this is just a little model of what a passive margin would look like. Deep sea fan, the abyssal plain out here in the deep,